So in this video, we are going to study the Kruskals algorithm for computing the minimum spanning trees for a graph. So what Kruskals? Let me write that first, right? Kruskals. What are we going to do? We are going to analyze. We are going to think about Kruskals algorithm. See how it was different from prim. We are going to prove the versus, let's say, prims. First of all, let me write that. Let me write the agenda of this video. Prove that Kruskals is indeed right. Correct, that is the algorithm. And how we will do that? We will the only way to prove any minimum spanning tree is indeed the minimum spanning trees. First of all, let's say we prove that it's at least a spanning tree. Then we'll say it's a minimum spanning tree. Then we'll see the algorithm and its running time, and if the initial runtime can be improved, initial to improved, and then you're going to study about union find data structure, which will indeed facilitate this improvement, right? So this is a 6-point agenda for this video. I'm going to place this paper here for your viewing, and let's go into the algorithm. So what prims does was, prims algorithm used to do what? For example, this is a graph. Choose any arbitrary vertex and whatever is cheaper, add it. And now in this connected component, whatever is the next cheaper edge in the frontier, add it. Next cheaper edge in the frontier, add it. Next cheaper edge, add it. Next cheapest edge, add it. And in that way, we have come to the prims algorithm. What Kruskals does is, Kruskals says that I don't give a shit about to maintain a connected component at all times. I have this graph. What I'll do is sort all of the edges, sort them. Whichever is the minimum edge in this particular sorted order, I'll add it. Whichever is the next minimum edge in this particular graph, I'll add it. Now you see, it need not be that at all times the Kruskals current state is connected, but we'll see in the future that in the end it will always result a minimum spanning tree. Whichever is the next minimum edge, we'll add it. Now let's say if the next minimum edge is this, and now the next minimum edge is let's say this one, this particular edge. My black pen is not working, but you get the point. If let's say this was the next minimum edge, adding this results in creation of a cycle. So Kruskal said, no, we're not going to do that. Add edge as long as no cycle. As soon as cycle, throw it. So it seems a pretty straightforward greedy algorithm sort of paradigm. Sort edges in their order from smallest to largest and start chewing lowest cost edges one at a time, and as long as there are no cycles, it seems very intuitive that this will always be right. But let's prove it formally, because it is indeed possible that by adding this, let's say if this was a sorted order, and by adding this edge, and if I were to add this edge, it would create a cycle, and hence I omit this, but adding this edge and this edge. But it is possible that there could have been an instance in which this edge was added, and it could have been another spanning tree as well. So let's think about Kruskals algorithm. So let's prove. I'm sorry. Let me trace back, and let's first of all write the Kruskals algorithm. Mr. Kruskal says sort edges 1 to m edges. Now for I going from 1 to m, before sorting you also have a S, which is the state of the system, which is empty. That means no edges are added. Now if S union I has no edges, no edges, S equals to S union I, and there is no else, because if S union I has edges, not go into this and move on to the next stage. Basically, this is it. This is simply the Kruskals algorithm. It seems very simple on pseudocode, everything does, but let's think about how we'll go and implement this. First of all, sorting edges, straightforward. I went from 1 to m. S union I has no edges. This is going to be a tricky part. This is going to be how to check whether edges or not edges. And S union I is another simple thing to do. So first of all, let's see if Kruskals algorithm is indeed correct. For that, what we are going to do is, first of all, prove, like I mentioned, that it is at least a spanning tree. So the properties of a spanning tree is these 2 points: has no cycle and is connected, right? So has no cycle, that's straightforward because it has no cycle. That is how the algorithm is designed. If it has a cycle, chuck it. I mean, if an edge were to have a cycle, we throw it away. So it definitely has no cycle. This is checked. Connected. To see if a graph is connected, what we do is look at all of its cuts and see if there is an empty cut. So if there was an empty cut, that means there are two distinct halves of the graph, one here, which are not connected by any edge. So let's say I have a particular cutting of a graph, this one and this one, and there are some edges. So let's say black edges, which are very faint, and a red edge, whatever. Let's say that red edge is the cheapest edge. So in an instance where there was the algorithm is just growing out of it, you know, if this was an empty cut of the Kruskals algorithm, for example, let's say Kruskals algorithm returned this to me with no edge crossing this frontier, no edge crossing this, I'm going to go to the Kruskals algorithm and I'm going to say you are not completed, because there is still an edge. By that, when I add that edge, no cycles are created. So hence the algorithm does not terminate in such a case. You know, I hope I'm able to convince you that. So when Kruskals algorithm is running and it encounters these edges, you know, red edge being the first one in a list of edges, because red is the cheapest one and this is a sorted list sort of, the red edge being here and the black edges being here, and none of these edges were previously considered, because as I said, this is an instance where there are no edges crossing a cut. So this is a intermediate instance of our algorithm, and hence the red edge is being the first one considered and none of the black edges were considered yet, and this is an empty cut. So Kruskal algorithm will look at the red edge, it will go to this particular number. If S union I has no edges, so S union this red edge, does it have an edge? Does it have a cycle? Sorry, no cycles. If I was calling that edges up till now, please forgive me. If S union I has no cycles, then we'll add it, and if it has a cycle, then we'll forget about it. So anyway, S union this red edge, does it have a cycle? It cannot have a cycle, because if it were to create a cycle, there would have been at least one edge also crossing this particular frontier, because that's how the double crossing lemma tells me. That's what the double crossing lemma tells me, that if you were to have a cycle in this, there must be another cycle, another edge crossing this too. But as this is the first edge and as this was an empty cut, this adding this red to this particular thing has no cycles whatsoever, and hence in that way the Kruskals algorithm will always return a connected graph, because if it were to return a disconnected graph, that means the algorithm is not completed yet. If let's go in another route, let's say I'm going to prove this, that it is always a connected graph by contradiction. Let's say Kruskals algorithm returns me a disconnected graph, that is, it returns me two distinct halves. That means this is a disconnected graph, and Kruskals algorithm returns this to me. That means in edge I to M, there is at least one edge. There is one edge at least that by adding that edge, I have not created any cycles. And by assumption, it has to return a graph which, I mean, not by assumption, I mean this for loop is yet to go one iteration more, and hence in that way the Kruskals algorithm did not terminate at all. So hence a contradiction. So that it cannot return a disconnected graph. So check. So has no cycle and is a connected graph at all times. Next we are going to look at this, that it is a minimum spanning tree, and for that we are going to go to our trusty old cut property. Right? So the cut property says is that if edge E is the cheapest in a cut AB, let's say, if edge E is this and it is the cheapest edge crossing cut A and B, then edge E must be in MST. Now if you think about it, Kruskals algorithm is very well poised for this. It seems like the cut property is and Kruskals algorithm are a match made in heaven, because Kruskals algorithm at all times only chooses the one which is cheapest edge, which does not create cycles. That's how Kruskals algorithm is designed, sorting the edge smallest to greatest, and if adding the smallest edge does not create a cycle, then it must be in that. So let's think about it for a second. So let's say we have a graph like this, let me create a few points, and this is how Kruskals algorithm starts. I created a lot of points, but never mind. So let's say the first edge that Kruskals algorithm added was this one, then the next was this one, then this one, and perhaps this one, then this one, and then perhaps this one, then this one, and now we freeze. It is an arbitrary freeze. It could have been any instant. And now I'm going to note, or let's say I'm going to keep track of the connected components that we have. This is one connected component, 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 and all of the other vertices in themselves are two connected component. Now let's say the next cheapest edge that created that is in our consideration is, let's say, this edge. I'm not going to mark it, but let's assume this. As it creates a cycle, Kruskal will ignore it. Let's say the next cheapest edge was this edge. It creates a cycle, Kruskal will ignore it. Let's say now, for the meat of the argument, let's say the next cheapest edge to be present is this particular edge. Does it create a cycle? No, it does not. So there exists a cut. I'm going to draw it with a red pen. There exists, let's say, any cut that goes through this, this one, and so here is an A and here is a B. As this is the next cheapest edge whatsoever in our entire algorithm, in our entire set of edges, this is the cheapest edge, so it is definitely the cheapest edge crossing A and B, right? And because it is the cheapest edge between A and B, it must be present in the MST. That's what the cut property says. That is what the cut property says. Think about it for a second. The cheapest edge, this edge of a cut, must be present in the MST. So at all times, whichever edge Kruskals algorithm is choosing, I'm going to say this. Whichever edge Kruskal chooses is the cheapest edge of at least one cut of the graph, right? So whichever edge Kruskal chooses is the cheapest edge of at least one cut of the graph, and by the cut property, that's all the cut property needs. And by the cut property, and I'll invoke the cut property on this, that edge must be in MST. So every edge chosen by Kruskal is justified by the cut property and hence must be in the MST, and hence Kruskal returns a minimum spanning tree. So let's spend some more time on the minimum spanning argument. Let's say if I were to choose such an edge which is, for example, I want to do this for myself, like this edge was present and this edge was present and cheaper than this edge too, but we ignored those edges. So what I can do is, for example, in an instant, let me draw it in such a fashion. All I have to do is show existence of one cut. So here's my question, here's what I'm thinking. For example, the two black edges which created cycles and hence were ignored in the Kruskals algorithm are the cheapest edge, 1 and 2. But Kruskal chose this edge. I colored it in blue. So yeah, Kruskal chose this edge and henceforth whatever. I have to show that this edge is at least cutting one particular, it is the cheapest of one particular cut. So what I can do is all of the edges before the blue one, the one which we are choosing, all of the edges before this, we're going to put it in one side of the cut. So in that way, this is essentially what I've done. This black edge was here and another black edge was here, but I chose my cut in such a way that I excluded both of these edges in the cut and I put them on one side, and hence this was by default the cheapest edge of this cut. So if although the next edge we are choosing is not the cheapest edge in an array, in the end the way we are going to implement it is in the form of a array loop, and although this edge is not the cheapest one in the array, this is definitely definitely the cheapest edge crossing some cut. And how do I find what is the hypothesized, what is the cut in theory? Take all of the edges before this, the ones which created cycles, put them in one side of the cut, and all of the rest put them in the other side of a cut, and hence this now becomes the cheapest one in that particular cut, and hence got that. Seems fair enough. So Kruskals algorithm is correct. Let's loop back on it. Kruskals algorithm is have a phi which is empty set, sort edges 1 to m for I going from 1 to m, union S union I as long as there are no cycles. I'm sorry about that. Yeah, S union I as long as there are no cycles. As soon as there are cycles, just ignore them and then keep on doing that until terminated, and by that you'll always return a connected graph. Has no cycle is always connected, and hence a spanning tree is a minimum spanning tree because every edge is justified by the cut property, and will always return a minimum spanning tree. So let's look at the algorithm and let's think about its running time algorithm, and now I'm going to talk about the run time. So for I going from 1 to m, first of all sorting, obviously sorting will take me m edges, so m log m, but m, the number of edges, is always less than nc2, so m is about less than n square, so log m, order log m is equal to order log m. So I can write this sorting as m log n. I just want to do that for the sake of it because m log n is generally the way graph algorithms are analyzed anyway. So for I going from 1 to m iterations, so that's noted, order m iterations. In each iteration what I do is check for cycles. S union I has cycles, question mark. That's the question, that's the thing I ask my computer. And how do we check for cycles? This is the question. How do we check for cycles? Perhaps use a breadth first search or depth first search, but using a breadth first search or a depth first search is going to take order of n time, n for each and every node it visits. So this entire loop will take order mn time, and hence our initial runtime. This was page number. This was page number 5. So our initial runtime is order of m log n plus order mn, and so order mn. This is what a naive implementation using breadth first search or depth first search to check cycles results in a running time of order mn. So now I can't do anything for this. I mean, there is no improvements in sorting. And as Professor Tim says, any good algorithm designer should always ask the question, can we do better? So I'm asking that question, can we do better? I can't do better on sorting for sure. Although let me try and think if I can somehow do this. If I were to have a way to do order 1 cycle checks, then I'll have, instead of order n time for breadth first or depth first, I will have order m and overall order m log n. I can't do anything for the m algorithm, the m iterations too. So this is the only way for improvement. If I can do some checks, cycle checks which are cheaper. So here is the idea. Let me take a new page for it. Here is the idea. Use a data structure, that is union find. Union find data structure is the name of the game right now. So what union find data structure does is it's a reason for existence, raison d'etre. Reason for existence. It's to maintain a partition. A partition in a universe. So this is how it looks basically. If this is my universe, or in our case, the number of nodes and edges, here is a partition C1, here is a partition C2, C3, C4, and let's say this is C5. All these are 5 partitions in a universe, and that's what union find data structure is cares about. What its operations are: union and find basically. So find operation, when you pass it a node, let's say X, it will tell me basically in which partition does this lie. So it will tell me one of C1, C2, C3 or C5, and then union. So find operation is pretty straightforward. I have an X, now it will tell me which partition X lies in, and union takes 2 arguments, Ci and Cj, and merges Ci, Cj together, merges Ci and Cj. So union C1 and C2 in our example will look something like this. This was used to be C1 and C2, but now they are both combined and we can call them whatever. C star, C2, C3, C4. So this is a new unionized C1 and C2 version. So this is basically what union find does. How can we use it for our purpose? Let's look at an overall level. I have n, let's say first of all I have n partitions for n nodes. N nodes, n partitions. I have an edge. Let's say when I'm going in the loop, when I'm in the loop for I1 to m, I have an edge, let's say I, which has one endpoint u and one endpoint v. So this edge uv. I say find u, find v. Now if u and v were to be in a same partition, that means u and v are in the same partition in the graph, and if I were to add an edge I, that is if I were to add edge I uv, it will create a cycle. So if find u and find v are 2 different answers, just a minute. So find u and find v are 2 different answers. That means they are not in the same partition, and adding this I, edge I, will not create any loops. And so what I do is then I go ahead and unionize these 2. So what happens is I'll take another page and let me write it in a proper fashion. If find u is not equal to find v, add I to S and then union of whatever this was, C of U and C of V, which is basically find U and find V to in a sense. So add I to S, and then for every edge I, find its U and V. I mean its two endpoints U and V. Find U. If they're not equal, that means by adding this edge I to S, it will not create any cycle because they are in the different partitions. So this is what union find data structure cares for, and this is what union find data structure is made for. Now we'll study union find data structure in a detail in a later video, and we'll see how to implement union find data structure and how to implement this union operation. That is also a main concern, and we'll see that how it is going to be so fast to do a find and union, and it's a really powerful and it's a really mathematically mind-blowing data structure. At least its running time analysis is.